In this video, we will use the concept of vectors to derive the beta coefficients for linear regression. We will also show you how to derive the exact result using calculus. And in the end, we will use gradient descent algorithm to solve the coefficients numerically. If you are new to linear algebra or numerical optimization techniques, I would recommend you to understand the basics first before you watch this video. Let's say we have a simple linear regression case where we want to predict sales Y given TV budget X. Here is a sample data with n equals to 20 data points. The ask is to estimate beta 0 and beta 1. In other words, find a straight line that best fits the data. Note that we are learning the parameters from a sample, so we only get the estimates of the parameters and not the true values. That's why I have put a hat on the parameters, because they are estimates. Let's write the sample regression equation. Here we are trying to get the best estimates for beta 0 and beta 1. Once we get the estimates for beta 0 and beta 1, we automatically get the estimate for the error term, or U hat, also called as residuals or fitted errors. Now let's make things simpler and drop the intercept term for now. Sales data and TV data are columns or vectors. How do we represent vectors graphically? With arrows. Note that these vectors are not two-dimensional as I have drawn them on the screen. They are actually 20-dimensional because there are 20 observations and each observation serves as a component of the vector. However, the dimensionality of a vector is never a problem as far as the vector maths is concerned, such as vector addition, subtraction, dot products, etc. So let's forget about the dimensions for a moment. If we look at the right side of the equation, the first term is beta 1 times TV. It simply means that we are scaling the TV vector by beta 1. The second term is whatever we need to add to this to make the resultant vector match sales. This is given by this joining vector. When a different estimate for beta is obtained, the residual vector also changes. How to estimate beta 1? One objective could be to minimize the length of the residual vector. That's kind of intuitive. So now let's have everything in one place. Assume that beta 1 hat is 0.06 for now. The first table has the data for sales and TV as originally observed. The second table shows how the sales is broken into two components. The first column is beta 1 times TV, which is the estimate of the systematic component. The second column is the residual, which is the estimate for the idiosyncratic component of sales. Note that once we fix beta 1 hat, residuals are automatically calculated by subtracting the systematic component from sales. I have also calculated the length or magnitude of the residual vector by taking square root of the sum of squared residuals, otherwise known as L2 norm. On the right side, we have the vector diagram for the same. Right now, beta 1 is 0.06 and the length of the residual vector is about 30.8. I'm going to change beta 1 slowly and we are going to keep an eye on the length of the residual vector. When I increase beta 1, I see that the residual vector is getting smaller and smaller. Wait, it looks like the residual vector starts getting bigger after one point. So we go back and right about there, the residual vector has minimum length. and we can see that the estimate of beta 1 is 0.094. Excellent. Not difficult to see that the residual vector is smallest when it's perpendicular to the TV vector. In that case, beta 1 times TV becomes the projection of sales on TV vector. Perfect. Now let's derive the exact mathematical formula for beta 1 hat. First off, when we minimize the length of the residual vector, we minimize the L2 norm, which is the square root of sum of squared residuals. We can ignore the square root for optimization purpose, as the solution will be the same. This objective function has a name. It's called as the OLS estimator. OLS stands for ordinary least squares. We want to find beta 1 hat such that the sum of squared residuals is minimized. Just to ensure we are not losing track of how we envisioned this task originally, here is a sample plot of 5 data points between y and x. Trivial point here to note that the line passes through origin because we dropped the intercept term beta 0. So OLS estimator will fit the line in such a way that the sum of these 5 squared residuals is minimum. Now we can solve this optimization exercise using calculus or any numerical procedure such as gradient descent. Or we can use the intuition that this will be minimum when the residual vector is orthogonal to the TV vector. If the residual vector is perpendicular to the TV vector, then the dot product must be 0. Note that beta 1 is a scalar in our case. So simplifying this, we get the closed form formula for beta 1. We can stop here, but let's do some more changes to this expression. We'll see why. If we treat these vectors as one column matrices, then we can write it in another form. Remember, sales is our y and TV is our x. So this formula for beta 1 hat is of the form x transpose x inverse x transpose y. The reason for doing this is that this formula is not a special case for simple linear regression. It's actually the closed form for OLS estimates for multiple regression as well, where X is the design matrix. The purpose of this exercise so far was to bring up the vector ideas into the derivation in the simplest way possible. Next, let's add back the intercept term that we dropped earlier and use calculus to arrive at this result. With the intercept term, our sample equation is this. Notice that our objective now involves searching for both beta 0 hat and beta 1 hat, which will together minimize least squares. The sum of squared residuals is also abbreviated as SSR in textbooks. Sometimes it's also called as RSS, which stands for residual sum of squares. For the purpose of deriving a formula, let's use x and y. Now to minimize SSR, we need to take the first order partial derivative of this expression with respect to beta 0 hat and beta 1 hat and set them as 0 separately. So we have two equations and two unknowns. We can easily solve them. But wait, there are useful insights in these equations. Equation 1 reduces to this. This means that the sum of residuals is 0, or you can say the average of residuals is 0. Equation 1 also leads to this, which means that the OLS line passes through the sample mean of x and y. It means the sample average of x and y will lie on the OLS line. Equation 2 shows that the residuals are fitted in such a way that the residual vector is perpendicular to x. This confirms our intuition. Note that all these results are enforced by the OLS estimator, meaning when we use OLS estimates for betas, we land with these results as a byproduct. Here is the summary of the results so far. From 1 and 3, we get the estimate for beta 1, and then using 2, we get the estimate for beta 0. For our dataset, the exact estimates can be found by first finding out the sample mean for x and y, then find the sum of squared distance of each x from average x, which is the denominator of beta 1, find the numerator of beta 1, then solve for beta 1, and then solve for beta 0. Let's try to match this result using the matrix-based formula that we derived earlier. In case of simple linear regression, y is a vector and x is the design matrix, which look like this. X transpose x gives us a cute little 2x2 matrix. Inverse of a 2x2 matrix is super easy. Now x transpose y gives us this. So we put everything into the main formula, which is x transpose x inverse x transpose y, and we get this expression. Note that this formula returns the beta hat vector, so we have to extract the individual estimates from this vector. There is one tiny elimination step left to do, which will exactly match the formula on top and at the bottom. So I will leave that as an exercise for you. How to derive the OLS estimates in multiple regression setup. Let's do this for 2 variables so we can see everything in a plot while we go through the maths. For more variables, the maths will not change. So here is our sample regression equation involving 2 predictors. As usual, beta 1 hat times x1 plus beta 2 hat times x2 represent y hat, which is our fitted or predicted y. Let's investigate the right hand side. 2 vectors x1 and x2 define a plane, which is the span of these 2 vectors. Beta 1 hat times x1 and beta 2 hat times x2 is a linear combination of x1 and x2, and therefore will lie on the span of these 2 vectors. Whatever is needed to add to this vector to match y is our residual vector u hat. Obviously, when we learn different estimates for beta, y hat and u hat will change. How do we choose the right coefficients? Following the same intuition, we want to choose the coefficients in such a way that the residual vector is orthogonal to x1, x2 plane. Here is our design matrix and our observed y vector and our estimated residual vector. If u hat is perpendicular to x1, x2 plane, it will be perpendicular to both x1 and x2. So we can write the dot products as 0. The 2 vector equations can be combined into a matrix equation. Now our sample regression equation can be written using matrices as we saw in the previous video. Let's pre-multiply X transpose on both sides. Using the fact that X transpose U hat is 0, we get our formula for OLS as expected. Beta hat vector is X transpose X inverse X transpose Y. The same result can be obtained by minimizing SSR as well. As we wrap up, let's do this in the most general form of regression. So here is the equation with k regressors and 1 intercept. Now this is the population process. Feel free to pause and confirm the dimensions of various elements in this equation. Now here is the sample process. The only difference between the population process and the sample process is that everything is actual in population process, whereas in sample process only X and Y are actual, beta and errors are estimated. Now our OLS objective is to minimize SSR or sum of squared residuals. So taking partial derivative with respect to each of the k plus 1 beta coefficients, we get k plus 1 equations. The first equation, which comes from differentiating with respect to beta 0, is interesting. It actually says sum of residuals is 0, as we saw in case of simple linear regression. The next k equations that come from differentiating with respect to each of the k beta coefficients say that the residual vector is orthogonal to each of the k regressors. Now combining 1 and 2, we get the same matrix equation we just got. And we can use this along with the sample process equation as we did before and arrive at our favorite formula for OLS estimator. As we wrap up, let's do justice to how a machine learning student will approach this problem. For convenience, let's consider only one regressor. Machine learning students will view the sum of squared residuals as a cost function. The convention is to use 1 over 2 times n as a scalar multiple to this objective function, which really does not impact the solution. Then calculate the partial derivative of the cost function with respect to each of the parameters that we want to estimate, and then get the gradient vector. The cost function that we are using has a convex shape and it has elliptical contours. This is true because if you look at the cost function, the equation is of the form of an ellipse in terms of beta 0 and beta 1. The convex shape has a global minima right at the bottom of the surface. We will solve the optimization using gradient descent algorithm. So what are the steps? Step 1, we initialize a pair of values for beta 0 and beta 1. Step 2, then we descend iteratively with the help of gradient at each location. And then we stop when we reach sufficient number of steps or the objective function does not improve. We use a learning rate called eta to control the step size of the descent. If we take giant steps, then we might oscillate over the minima. That's not very good. On the other hand, if we take very small steps, then it'll take forever to reach the minima. That's all for now. Thanks for watching. If you liked the video, please subscribe to this channel to get latest educational content on statistics, finance, risk management, and analytics. Also, if you are a finance professional and looking for a certification in data science, log on to peakstotales.com and check out our prep course for Finance Data Professional, which is a global certification offered by FDP Institute. Experience a new way of learning complex mathematical and statistical concepts with rich visualization in an easy-to-follow Microsoft Excel-based environment. Take advantage of our mind maps and Excel-based hands-on modeling sessions.